Section: Introduction. In this section, we discuss how models that have been trained on large, general datasets have shown impressive abilities to adapt to a wide range of tasks, from understanding language to interpreting images and text together. To make these general models work well for specific tasks, a common approach is to fine-tune them, which means retraining all the model's parameters on a new task. However, as models and the datasets they learn from get bigger, fine-tuning the whole model becomes very expensive. To solve this problem, methods for fine-tuning that only adjust a small number of parameters have been developed. One such method, known as LoRA, stands out because it's simple and effective without changing the model structure. However, there's still a gap in performance between LoRA and full fine-tuning, which might be due to the limited number of parameters LoRA adjusts. We haven't fully explored other possible reasons for this gap. We've taken inspiration from a technique called weight normalization, which speeds up learning by reparameterizing weights in terms of their size and direction, to analyze how LoRA and full fine-tuning update model weights differently. Our analysis shows that LoRA and full fine-tuning change weights in very different ways, which we think reflects how well each method can learn. Based on our insights, we propose a new method called Weight-Decomposed Low-Rank Adaptation, DoRA. This method starts by breaking down pre-trained weights into their size and direction parts and then fine-tunes both aspects. Because the direction part has a lot of parameters, we use LoRA to make the fine-tuning process more efficient. Our experiments show that DoRA performs similarly to full fine-tuning in terms of learning ability but without making inference slower. We tested DoRA on a variety of tasks, including language understanding and image text tasks, and found that it consistently does better than LoRA without slowing down the model. Our main contributions are introducing DoRA, a new efficient fine-tuning method that uses weight decomposition to achieve learning performance close to full fine-tuning, a novel analysis that highlights the differences in how full fine-tuning and other efficient fine-tuning methods update weights, and demonstrating that DoRA outperforms LoRA across different tasks and model architectures without increasing the time it takes to make predictions. In related work, we look at other methods designed to fine-tune large models more efficiently by only adjusting a small subset of parameters. These methods can be grouped into three categories: adapter-based methods, which add new trainable parts to the model; prompt-based methods, which add trainable tokens to the input; and methods like LoRA, which adjust weights in a way that doesn't add extra time to making predictions. Our work falls into this third category, and we show that our method works well compared to LoRA and its variations through extensive testing. Section Summary. In this section, we introduce Weight-Decomposed Low-Rank Adaptation, DoRA, as a novel parameter-efficient fine-tuning, PEFT, method that incorporates weight decomposition to achieve a learning capacity similar to full fine-tuning, FT, without additional inference latency compared to LoRA. Our analysis reveals distinct update patterns between LoRA and FORT, leading to the development of DoRA, which fine-tunes both magnitude and directional components of pre-trained weights, outperforming LoRA across various tasks without sacrificing efficiency. Section: Weight Decomposition Analysis. In this section, we delve into the concept of weight decomposition analysis. The research introduced in LoRA, Low-Rank Adaptation, suggests that LoRA can be seen as a broad approximation of the full fine-tuning process. By gradually increasing the rank, denoted as R, of LoRA to match the rank of pre-trained weights, LoRA can achieve a level of expressiveness similar to that of full fine-tuning, FT. Many previous studies have pointed out that the main difference in accuracy between LoRA and FT is due to the limited number of trainable parameters in LoRA, often without further investigation. Inspired by weight normalization, which breaks down the weight matrix into magnitude and direction to speed up optimization, we introduce a new method of weight decomposition analysis. Our method separates the weight matrix into two components: magnitude and direction. This helps us understand the fundamental differences in how LoRA and FT learn. Our analysis method looks at how the magnitude and direction of the weights in LoRA and FT change compared to the pre-trained weights. We break down the weight matrix, denoted as W, into a magnitude vector and a directional matrix. This ensures that each column of the directional matrix remains a unit vector, and the corresponding value in the magnitude vector indicates the size of each vector. For our analysis, we chose the VL-BART model fine-tuned on 4 image text tasks. We decompose the pre-trained weight, the fully fine-tuned weight, and the LoRA adjusted weight of the query value weight matrix. We then examine the changes in magnitude and direction at different training steps for both FT and LoRA. Our findings show that LoRA consistently exhibits a positive slope trend across all intermediate steps, indicating a proportional relationship between changes in direction and magnitude. On the other hand, FT shows a more varied learning pattern with a relatively negative slope. This suggests that while LoRA can adjust the magnitude and direction of weights proportionally, it struggles with making subtle adjustments. Specifically, LoRA is not as adept at making small directional changes alongside significant magnitude changes, or vice versa, a capability that FT possesses. We believe this limitation of LoRA may be due to the complexity of learning both magnitude and directional adjustments simultaneously. To address this, we propose a variant of LoRA, called Weight-Decomposed Low-Rank Adaptation, DoRA. DoRA starts by decomposing the pre-trained weight into magnitude and directional components and fine-tunes both. Since the directional component involves a large number of parameters, we further decompose it with LoRA for efficient fine-tuning. Our approach simplifies the task by focusing LoRA on directional adaptation while allowing the magnitude component to be tunable. Additionally, decomposing the weight into magnitude and direction makes optimizing directional updates more stable. It's important to note that the main difference between DoRA and weight normalization is in their training approaches. Weight normalization trains both components from scratch, which can be sensitive to initial conditions. In contrast, DoRA starts with pre-trained weights, avoiding issues with initial conditions. We initialize DoRA with pre-trained weights, keeping the directional component frozen and making the magnitude vector trainable. The directional component is then updated through LoRA. Our analysis of the query weight matrix changes in DoRA and FT shows that, unlike LoRA, DoRA and FT have a negative slope. This suggests that FT tends to make significant changes in either magnitude or direction, which is sufficient for adapting to downstream tasks. Our findings also show that both FT and DoRA have a negative correlation between changes in direction and magnitude, while LoRA has a positive correlation. This indicates that DoRA, with its ability to make significant directional adjustments with minimal changes in magnitude, or vice versa, has a learning pattern closer to FORT, demonstrating a superior learning capacity over LoRA. Section Summary. In this section, we introduce Weight-Decomposed Low-Rank Adaptation, DoRA, based on our weight decomposition analysis findings. DoRA decomposes pre-trained weights into magnitude and directional components, focusing on fine-tuning both separately. By simplifying LoRA to concentrate solely on directional adaptation and keeping the magnitude component tunable, DoRA shows improved learning capacity resembling that of full fine-tuning, FT, outperforming LoRA in making substantial directional adjustments with minimal magnitude changes. Section: Gradient Analysis of DoRA. In this section, we delve into the gradient analysis of DoRA and explain how our proposed method of breaking it down helps in optimizing the change in V, denoted as delta 5. We start by looking at how the gradient of the loss function, L, changes with respect to M and the updated V, which we call V prime. V equals V plus delta 5. We find that the gradient of the weight, when updated, is influenced by two main factors. It's scaled by the ratio of M to the norm of V prime, and it's directed away from the current weight matrix. These factors help make the gradient's covariance matrix more similar to the identity matrix, which is good for optimization. Moreover, since V prime is just V plus delta 5, the gradient with respect to V prime is the same as the gradient with respect to delta 5. This means all the optimization benefits we get from breaking down the problem in this way fully apply to delta 5, making the learning process of DoRA more stable. To understand how DoRA learns, we look at the gradient from another angle. We simplify our notation by using lowercase letters for vectors. We consider an update to a weight vector, W double prime, W equals W plus delta W, where delta W is proportional to the gradient of the loss with respect to W. We imagine two scenarios, S1 and S2, where S1 has a smaller directional update compared to S2. Assuming the magnitude of delta W is the same for both scenarios, and initially, delta V is 0 and V prime is just V, we find that the cosine of the angle between delta W in S1 and W is larger than in S2. This implies that the updates in S1 are more aligned with the original direction of W than those in S2. We further analyze this by considering the magnitude scalar of vector W, denoted as m star. Given that the magnitudes of delta W for S1 and S2 are the same, and so are the magnitudes of the gradients of the loss for S1 and S2, we conclude that the magnitude of the gradient with respect to m star is larger for S1 than for S2. This means S1 has larger magnitude updates but smaller directional changes compared to S2. Our observations are supported by empirical evidence, showing how DoRA can adjust the learning pattern to be more aligned with fine-tuning methods rather than LoRA. Moving on to reducing training overhead, we note that the gradients of W prime and delta W are initially the same. However, with DoRA, which focuses on the directional component of the low-rank updates, the gradient of the low-rank updates is different from that of W prime. To manage this, we propose treating the norm of V plus delta 5 as a constant during backpropagation. This means it reflects the updates of delta 5 but does not change during backpropagation. This approach significantly reduces the memory needed for the gradient graph without affecting accuracy much. We tested this modification on fine-tuning Llama 7B and VL-BART and found it reduces training memory by about 24.4% for Llama and 12.4% for VL-BART, with minimal impact on accuracy. For detailed comparisons of training memory usage and accuracy, please refer to the table in the appendix. Following these results, we include this adjustment in all further experiments with DoRA. Section Summary. In this section, we derive the gradient of DoRA and explain how our proposed decomposition enhances the optimization of delta 5 by analyzing the gradient's behavior. We observe a negative slope in the learning pattern of DoRA, which aligns the gradient's covariance matrix closer to the identity matrix, aiding in optimization. Our approach transfers optimization benefits to delta 5, improving the learning stability of LoRA by adjusting the learning pattern to align more closely with that of FORT. Additionally, we reduce training overhead by detaching vert V plus delta vert underscore C from the gradient graph, significantly cutting down memory consumption during backpropagation without compromising accuracy, as demonstrated in our ablation study on Llama 7B and VL-BART. Section: Experiments. In this section, we delve into a series of experiments to demonstrate the effectiveness of our method, DoRA, across various tasks that span language, image, and video domains. Initially, we compare DoRA with other methods designed for parameter-efficient fine-tuning, PEFT, by applying it to the Llama 7B, 13B models for common-sense reasoning tasks. We then broaden our scope from focusing on a single type of data to handling multiple types, such as images and videos alongside text. In this context, we compare DoRA with another method called LoRA, using the VL-BART model for multitask image, video text understanding tasks, and also for visual instruction tuning with the LLAVA 1.5 to 7B model. We further investigate how well DoRA works with LoRA and another method named VERA for instruction tuning tasks using the Llama 7B and Llama 2 to 7B models. Through a series of detailed tests, we show that DoRA outperforms LoRA in terms of performance, regardless of the number of samples used for fine-tuning or variations in the model's rank. We also explore how DoRA can achieve higher accuracy than LoRA with fewer parameters that need to be adjusted, by focusing updates on specific directional components within certain modules. Focusing on common-sense reasoning, we assess DoRA against LoRA and several baseline methods, including different types of learning strategies like prompt learning, series adapter, and parallel adapter, using the Llama 7B, 13B models. We also compare these results with the accuracy of ChatGPT, obtained through a specific API, on a zero-shot chain of thought task. The common sense reasoning evaluation involves 8 subtasks, each with its own set of training and testing data. We combine the training data from all these tasks to form a comprehensive training dataset and then evaluate the models on each task's testing data separately. To ensure a fair comparison, we start by fine-tuning the models with DoRA using the same configuration as LoRA, only adjusting the learning rate and slightly increasing the number of parameters to include learnable magnitude components. We also experiment with a version of DoRA that uses half the rank compared to LoRA, referred to as DoRA-dagger. Our findings reveal that DoRA consistently outperforms all baseline methods on both the Llama 7B and 13B models. Notably, DoRA improves accuracy by 3.4% over LoRA on the Llama 7B model, surpassing even ChatGPT's accuracy levels. On the Llama 13B model, DoRA not only outperforms LoRA by 1% but also achieves comparable accuracy to the best baseline method, with significantly fewer parameters and without adding extra computational costs. The DoRA-dagger configuration further demonstrates the efficiency of DoRA, achieving better performance than LoRA with only half the number of parameters. Moving on to image-video text understanding tasks, we aim to see if DoRA remains competitive in multimodality fine-tuning tasks. We compare DoRA with LoRA and full fine-tuning on the VL-BART model, which includes a vision encoder and an encoder-decoder language model, across various tasks related to image and video understanding. Following the established framework, we fine-tune VL-BART for both image and video text tasks within a multitask framework. Our results show that DoRA consistently outperforms LoRA in accuracy across all tasks, maintaining a similar number of trainable parameters. Specifically, DoRA surpasses LoRA's performance by nearly 1% in image text tasks and by approximately 2% in video text tasks, reaching the accuracy level of full fine-tuning in some cases. Section Summary. In this section, we conduct a range of experiments to demonstrate the effectiveness of DoRA in various tasks spanning language, image, and video domains. We compare DoRA against different methods like LoRA and parameter-efficient fine-tuning, PEFT, on tasks such as common sense reasoning and multitask image, video text understanding, showcasing that DoRA consistently outperforms LoRA in performance across different scenarios, even with fewer trainable parameters. Section: Visual Instruction Tuning. In this section, we delve into the process of enhancing visual instruction tuning by increasing the size of our model and comparing our method, DoRA, with LoRA and traditional fine-tuning, FT, techniques. We utilize a model known as LLAVA 1.5 to 7B, which combines a language model, Vicuña -1.5-7B, with a vision encoder, ClipVit-L 336px. The training data we use comes from a variety of sources, including visual question answering, VQA, optical character recognition, OCR, region-level VQA, visual conversation, and language conversation datasets. We adopt a specific approach to filter the training data and format the tuning prompts. For a fair comparison, we ensure that DoRA follows the same setup as the LoRA configuration. We then evaluate the fine-tuned models across 7 vision language benchmarks, including VQA version 2, GQA, VisWiz SQA, VQA Text, POPE, and MMBench. Our observations reveal that LoRA's average accuracy already exceeds that of FORT, suggesting potential overfitting issues with FT. Although DoRA is designed to boost LoRA's performance to more closely match that of FORT, in cases where FT falls short of LoRA, the enhancements offered by DoRA may not be as significant. However, DoRA still outperforms both LoRA and FORT, showing an average improvement of 0.7% over LoRA and 1.1% over featuring. We also explore DoRA's compatibility with other LoRA variants. Specifically, we look at how DoRA can adapt the concept of incremental directional updates, a technique that can be swapped with different LoRA variants. We choose VERA as a case study for this exploration. VERA's strategy involves freezing a unique pair of random low-rank matrices across all layers and using minimal layer-specific trainable scaling vectors for incremental updates. This significantly reduces the number of trainable parameters by 10 times compared to LoRA, with only a slight impact on accuracy. We apply this strategy with DoRA, naming the combination DoRA, and assess its effectiveness alongside DoRA, VERA, and LoRA on the Llama 7B and Llama 2 to 7B models, focusing on instruction tuning with a subset of the cleaned Alpaca dataset. Our findings, based on the MT-Bench benchmark and evaluated by GPT-4, show consistent improvements of our proposed methods over VERA and LoRA for both model versions. Furthermore, we investigate how DoRA performs with varying amounts of training data, a crucial factor since access to large fine-tuning datasets can often be limited. We compare DoRA with LoRA and DoRA with VERA across different instruction tuning sample sizes, ranging from 1,000 to 10,000 samples. Our results demonstrate that DoRA and DoRA consistently outshine LoRA and VERA across all sample sizes. For example, with 7,000 samples, DoRA and DoRA surpass their counterparts by margins of 0.3 and 0.33, respectively. This trend holds even with as few as 1,000 samples, where DoRA and DoRA maintain their lead. These findings underscore our method's ability to consistently improve performance over LoRA and VERA, regardless of the training sample volume. Section Summary. In this section, we scale up the model size and compare DoRA to LoRA and FT on visual instruction tuning tasks using LLAVA 1.5 to 7B, which includes a language model and a vision encoder. We observe that DoRA demonstrates superior performance over both LoRA and FORT, with an average improvement of 0.7% over LoRA and 1.1% over FORT, suggesting that DoRA can enhance LoRA's performance. Additionally, we explore DoRA's compatibility with other LoRA variants like VERA, showing that DoRA merges the advantageous qualities of DoRA and VERA, achieving scores on par with or surpassing those of LoRA with significantly fewer parameters. Section. Robustness of DoRA towards different rank settings. In this section, we delve into how different rank settings affect the performance of DoRA and LoRA. We experimented with various ranks, specifically 4, 8, 16, 32, and 64, to see how they influence the outcomes of fine-tuning the Llama 7B model on tasks that test common-sense reasoning. We've illustrated the average accuracies of both LoRA and DoRA for these ranks in a figure, and provided detailed data in a table for a clearer comparison. From our observations, it's clear that DoRA consistently outperforms LoRA across all the rank settings we tested. This difference is especially pronounced at lower ranks. For instance, when the rank is set to 8, LoRa's average accuracy falls to 40.74%, and it drops even further to 39.49% at rank 4. On the other hand, DoRA maintains a much higher accuracy, achieving 77.96% at rank 8 and 61.89% at rank 4. These results highlight DoRA's robustness and its ability to maintain superior performance over LoRA, regardless of the rank setting. Moving on to the analysis of tuning granularity, our visualizations show that significant changes in magnitude often lead to relatively minor directional changes. This observation, coupled with the fact that most of the trainable parameters are due to directional updates, prompted us to investigate if we could reduce the number of trainable parameters. Specifically, we looked into whether updating only the magnitude components of certain modules, while still updating both the magnitude and directional components of other linear modules, could be effective. Our findings reveal a notable difference from the original configuration recommended for LoRA, which suggests updating both the multi-head attention and MLP layers for optimal results. In contrast, DoRA can achieve higher accuracy by updating only the directional and magnitude components of the multi-head layers and the magnitude components of the MLP layers. According to the data shown in our table, by focusing updates on the directional and magnitude components of the QKV modules and only the magnitude of the rest of the layers, DoRA not only surpasses LoRA by 2.8% on Llama 7B and 0.8% on Llama 13B, but also does so with less than half of the trainable parameters compared to LoRA. This approach underscores DoRA's efficiency and effectiveness in achieving superior performance with a more streamlined parameter update strategy.